All right, on this first one, we've got two examples. So you should notice that we are starting at 100 for the reactants for how much energy they have, and products are going to have about 300 kilojoules of energy coming out. So first question, products have more energy than the reactants, so that means that energy must be gained in the system. If there's more energy at the end, then we would have a positive delta H, which means that our reaction is endothermic. So remember that if we calculate delta H, it is the product's energy minus the reactant's energy. So we would have 300 minus 100. And so that would give us a delta H of 200 kilojoules. And if we are gaining energy, then it is an endothermic reaction. Example 2 is the exact opposite. Our products here have less energy than the reactants, and so energy is lost out of the system, or it flows out of the system, and this would be an exothermic reaction. And so this reaction will feel warm to the touch because we'll feel the energy coming out of the reaction. All right, so one of the first things you should do on this problem is make sure that you have defined these different vocabulary words here using the notes and the video from earlier. And then the first example here shows you how to do each of these problems. So here's what we're going to be doing. For each problem, on A, you are going to calculate the activation energy. So on the first one, you can see that activation energy is going to be taking the energy of the reactants and how much energy does it take to get the reactants up to this plateau right here. So we can see for A's example, we take the energy of the plateau, 150, minus the energy of the reactants, 50, and that means that it takes 100 kilocalories of energy in order to activate this reaction. Letter B, which is the second thing you're going to do, is you're going to calculate the delta H of the reaction. So remember that delta H of the reaction is going to be your energy of your products minus the energy of the reactants. And so our products energy is 100, which we can see right here, and our reactants energy is 50, which we can see right here. So we take 100 minus 50, and our delta H is 50 kilocalories per mole. And then finally, the last thing you're going to do for each problem for C is you're going to determine if it's exothermic or endothermic. So remember that if energy is being lost, then it's going to be exothermic. So exothermic, energy is lost and given off, and so we get a negative delta H, so that would be exothermic. And if it is endothermic, we have a positive delta H. So since this is positive right here, that's going to be an endothermic reaction. Go ahead and try the other ones on your own, and then you can come back and check out the answers for each of them. All right, so here's the answers to the first one. You should be taking 500, which is the activation energy up here, and subtracting the energy that you began with the reactants, and that would be 500 minus 400, and you would, or 100, and that would be 400 kilojoules per mole. That's how you get activation energy. To get energy of the reaction, remember that our energy of our reaction is delta H. It is the energy of the products minus the energy of the reactants. So I did that for B right here. So our products are at 300 minus 100, so that would be 200 kilojoules per mole. And then since there's more energy at the end, that means that the reaction gained energy, didn't give it out. And if we gain energy, it's endothermic, or if our delta H is a positive number like we see here, then it is going to be endothermic. So for each of these, make sure that you follow the instructions. Please remember that for A, you're finding the activation energy. So you're going to take the energy when it's activated and subtract the energy when it begins. That's how you're going to do A for all of them. The energy that when it's activated minus the energy of the reactants. So energy once it's activated minus the energy of the reactants. That's going to be A for you. For B, for each of the problems, we want to find delta H. So remember that for B, for delta H, you're going to take the energy of the products minus the energy of the reactants. So product's energy minus reactants. Product's energy minus reactants. Product's energy minus reactants. And then for C, you're going to say if it's endothermic or exothermic. So remember that if it is exothermic, then you should have gotten a delta H that is negative, which means that energy is lost, energy is released. So basically, you should be looking for when your products have less energy than you started. That's going to be exothermic. If it's endothermic, then we gained energy in the reaction. And if we gained energy in the reaction, then our products are going to have more energy than when we started, and our delta H is going to be positive. So there's some clues for you for doing these. So on these problems, we're going to try to make our own potential energy diagrams. So it gives us all of our information right here, okay? And then we're going to be answering some questions. So the first one gives us the potential energy of the reactants is 250. So we're starting with this much energy right here, 250. It says the energy of the activated complex is at 350. So that means when it's activated, it's up here at 350. So that means our activation energy itself is 100. So we're going up to there. Then the potential energy of our products is 300. So at the end, we're here. So you can see then that's what our graph will look like. Now, the first question it asks us is if this reaction is exothermic or endothermic. So if we think about our delta H, let's calculate that since it wants to know what the value of our delta H is. Remember, delta H is our products minus our reactants. And so our products have an energy of 300 and our reactants had an energy of 250. So our delta H would be positive at 50 kilojoules of energy. And so if it's positive, that means that this is endothermic. It gained energy. So, and we can see that if we look at our reaction, that we have more energy at the end than we started with. So our overall reaction gained energy for us. Then if we look at the next question, it says if a catalyst were added, what would happen to the diagram? Remember, if a catalyst is added, we're not going to change the energy of our reactant, so it's still going to be here. We're not going to change the energy of our products, so it's still going to be here. All we do is we lower the activation energy. So now maybe the energy of the reaction only has to come up to here in order to get the reaction to occur. And so we can see we've lowered the activation energy. So all we do is lower the activation energy. We do not have any change to the energy of the product or the energy of the reaction or the reactants. Okay, so no change to the energy of the products or the reactants. And I drew that in red on the graph so you can see. Go ahead and try the other portion of this worksheet on your own. See if you can draw that one on your own and answer the questions. You should be able to do most of these on your own too. The one thing that I want to point out is that the potential energy of the activated complex, that's the energy that we have all the way up here. And then the activation energy is how much energy it takes to get from our reactants all the way up to our products. So as you're working on that, pay attention to the wording. This one says potential energy of the products. So we just want to know when we draw on our graph the ending energy that we use, that we draw in from here. When it says potential energy of the activated complex, that's going to be the top of the hill. So our top of our hill is going to be here. The actual activation energy is the amount of energy it takes from the reactants to the products. So you might want to make yourself a note there. Activation energy is the energy to get from reactants all the way up to that top peak. And then the actual potential energy of the activated complex, that's the amount of energy when we're at that top peak, when we're activated already. So for this page, the one thing that I want to point out are some of the words here. So where it says energy of activation, again, that's how much energy you need to get from the reactants up to the peak where it's activated. Okay? The potential energy of the activated complex, that's the energy it has when it's all the way up at that peak. So if we were looking at a graph and it went like this, the activated complex, that's just how much energy is it here. Whereas the energy of the activation is how much energy does it take to get from here at the reactants up to that peak. Okay, so the energy of the activation is how much energy does it take to get from here to here, from the reactants to the peak. And the potential energy of the activated complex is just how much energy is there when we're at the peak. What is that number at that peak there? So that should help you a little bit with answering